this evening, we have John Davies, who joined the I4IS, which is the Initiative and Institute for Interstellar Studies, soon after it was formed in 2012. He coordinates schools and outreach engagement for I4IS and edits the quarterly magazine, Principium. John worked for Hawker Siddeley Dynamics Space Projects Division in 1968, working on the Blue Streak launcher and projects involving an astronomical telescope study for ESRO and NASA, which became the Hubble. Since then, he's worked on packet switching networks and continued for most of his career in system software development for communications. He's going to talk on the first steps to interstellar probes. And I should say that this lecture is a joint effort with the Herschel Society of Bath and the British Interplanetary Society. So let me hand you over now to John Davies.
Right, thanks very much. Can everybody hear me? And can you see my my introductory slide there? So this is first steps to interstellar probes, the I4IS Project Glowworm. So everybody got that? Okay, good. Right, so I'll get some details about Glowworm, but it's a near-term low Earth orbit demonstrator of laser push technology, and I'll get into a little bit of detail about that as we go through. So here's what I'm going to talk about. Why do we want to do this? A little bit of background about I4IS, some history, two very important people in the context of in particular interstellar, although both of them did many things in related space endeavors. Recent work, big and small, and you'll see that it's in this case it's very big, very small. And then the core bit about the Glowworm project itself and some conclusions, and then I'll talk a bit about I4IS Project Lyra, which is a rather more astronomical thing, which I will get to towards the end. So why do we want to do that low Earth orbit demonstration? Because laser sail propulsion is currently the most promising propulsion approach for interstellar probes. And we don't yet have a demonstration of it in space. It's been done in a vacuum chamber. You can point a laser at a reflecting sail in a vacuum chamber, but it's never been actually done in space, and that's what we're aiming to do. So we're talking about verification, and we're talking about validation, and then we're talking about testing. And we're aiming to increase the maturity of laser sail propulsion. And we're by no means the only organization working on that, but as far as I'm aware, we're the only one who has a demonstrator in vision, an in-space demonstrator. So who are we? From the UK point of view, we're the Initiative for Interstellar Studies. Interstellar Studies really in the UK, in the most serious work, dates back to the Daedalus project, and I'll say a little bit about that later on. But any BIS members who are watching here will probably be aware of what the Daedalus team did in the 1970s, and it has successors, which I'll say something about. Initiative and Institute for Interstellar Studies were founded as informal organizations in 2012. And incorporated in both in the UK as the initiative and in the USA, specifically the state of Tennessee, both in 2014. So we've been around for quite a long time. We've been around for about 8 years as coherent organizations, and for about 6 years as formal bodies. And we have people in many countries, and I'll say a bit about our activities in addition to Glowworm and Lyra and the countries that we're in. And the astronomical people among you will be familiar with the names Oumuamua and Borisov, I'm sure, are the first interstellar objects in the solar system that we're aware of. And I4I's Project Lyra, maybe some of you will know a little bit about, but I'll say a bit more about that than perhaps you know already. So who are Tsiolkovsky and Forward? I'll say a bit more about them in detail in a moment, but Konstantin Edvardovich Tsiolkovsky was a Russian mathematics teacher who was obsessed with the idea of humanity going into space. And that quotation of his is perhaps his most famous one. Earth is the cradle of humanity, but one cannot live in a cradle forever. If any of you saw the cosmonauts exhibition at the Science Museum in London a couple of years ago, you'll have seen that saying written in very large letters over the exit to the exhibition. His activities in this area are pretty diverse. He died in 1935, and he was quite old at that point. So he's really a Victorian era and perhaps to some extent just after that figure. And his equation is in essence what governs all forms of reaction propulsion rockets, essentially. And back in 1924, he was talking about different propulsion mechanisms. He talked about the beam of electric or even light, solar rays, should exert pressure. This method would seem to be the most refined. In essence, he was thinking about the use of photons for propulsion. And in fact, another Russian guy was the first to demonstrate that. It's a consequence directly, as I understand it, I'm not a physicist, but of Maxwell's equations. And it was actually demonstrated as a laboratory experiment as early as, I think, the very, very early 20th century by, I forgot the guy's name, but and what Robert Forward did quite a number of years later than that, in 1984, he was a physicist at Hughes Corporation, and he proposed solar system-based lasers to push large laser cell spacecraft over interstellar distances back in 1984. And you'll see a reference at the bottom to his famous paper, and also to an article in our quarterly magazine, Principium, about Tsiolkovsky's thinking in interstellar terms, dating back a couple of years. So we're talking about light sails here, and this is Robert Forward's light sail equation. So the acceleration of a vehicle of mass m and a reflectance eta, I think that is, driven by an incident laser power p, is alpha, the acceleration, is twice the reflectance multiplied by the power divided by the mass of the thing being propelled and the velocity of light. And of course, c, as I guess almost everybody here tonight will realize, is a rather large number. So you have to have a great deal of p on the top of that equation, and as little as possible of the m, given that you've got that c on the bottom of the fraction there. And of course, the reflectance has to be pretty close to unity, because if it isn't, and you're using very powerful beams of photons, then your vehicle will just be destroyed. So that's exact words lifted from Forward's 1984 paper. So what's been happening in terms of interstellar probes? It's not all light sail stuff. That's just the most promising thing recently. Project Icarus is the son of the BIS Daedalus project, and I'll say a little bit about at least one of the results from that a little later. I4IS got involved in laser push technology way back in 2014. We ran a competition, an international student competition, to design such a craft, and we had participation from University of California, Santa Barbara, who you'll see popping up later, University of Cairo, a consortium of French and British universities, and Technical University of Munich, who you'll see also popping up later in this. So that was interesting. That was a great coming together of undergraduate and postgraduate talent. And then I'll say a bit about the IFRS Andromeda study, which is an early laser sail study that was to some degree a descendant of the Dragonfly work. And then Breakthrough Starshot, which is where the big bucks have come and is largely American, although not exclusively. So here's Daedalus. This is the 1970s study. This is the Universal Adrian Mann, who is the guy who does the visualizations for so much of this stuff. Still does. And as you'll see, it's a two-stage vehicle. And the assumption that the guys back in the 70s had was that we will have successfully achieved inertial confinement fusion by the time such a vehicle could be built. And this is 50,000 tons built in space. You couldn't build it on the ground. So it's many decades away, and their assumption that inertial confinement fusion would be successfully achieved is probably correct. It's been pretty close to achievement at the National Ignition Facility in California for some time, and there are other experiments going on along similar lines. But it's not the only way of having fusion propulsion, but that's a reaction-based thing. And if you look at, again, at the work of Tsiolkovsky, his famous equation limits the extent to which rockets can achieve very large velocities. And the problem is essentially that you just cannot get the propellant that's powerful enough, and you've got to carry the propellant along with you. Much more about that. There's a BIS book that collects all the papers with respect to Daedalus. And anybody that's interested in that, I recommend just buying the book. It's not very expensive, and it's got everything in there. Here's the most developed of the various successor studies, which started in around about 10 years ago. The Icarus project, which was BIS, an organization in the USA called the Tau Zero Foundation, came together, and a number of design studies were done with different ideas as to how you might improve on the Daedalus idea. And this was one using Z-pinch, or Z-pinch, as the Americans call it. Two countries divided by a common language, as always. So this relies on the fact that an electric current generates a circular magnetic field around the conductor. And if the current is strong enough, as in the plasma in this case, then that circular field has a strong enough compressive effect to result in fusion of the plasma. And there is at least one experimental reactor in the USA using Z-pinch. So this is the work of Robert Freeland in the USA and Michel Lamontagne, who's a French-Canadian. And this is Michel's visualization of their vehicle. And the wings on it are not wings, they're radiators. And there's a story about the ship in 2001: A Space Odyssey that goes with that, but that would be a diversion. So this is 25,000 tons rather than 50,000 tons of Daedalus. So we're getting a little bit lighter, but this is still massive construction. And all has to be done in space, essentially. So what about laser cell propulsion? This is the light things. So solar photons have already been used in spacecraft, notably the Japanese probe Icarus is a solar sail probe. The Planetary Society in the USA have launched an experimental low Earth orbit satellite, lightsail 2, which uses the radiation from the sun to alter its orbit. But we go back to Forward's paper in 1984, and essentially it's just like that diagram, very, very simple diagram. and it's been tested in vacuum chambers, but not yet in space, and that's what Glowworm is aiming to do. Going back a little bit, back in 2016, the breakthrough initiative, Project Starshot, just before it was actually publicly announced, due to just a coincidence that a guy called Pete Warden, who's the director of the Breakthrough Starshot project, bumped into one of our founders, Kelvin Long, in California, and he was aware of the Glowworm study, and he suggested that I4IS technical people might produce a quick study of an interstellar probe driven by large-scale lasers. And within 3 days, we came up with the answer to that, and it still stands up, I believe. Laser cell propulsion, space-based, see a contrast with Starshot in a little while, about 1 gigawatt, and again you'll see a contrast with the Starshot proposals. 50-year time of flight, relatively conservative, about the same time as Daedalus. 10% of light cruise velocity, aimed at Alpha Centauri. That's the obvious place to go to first. Gram scale mass, and using a radioisotope thermal generator for onboard power. So that's the essence of that project. There's a lot of references at the end of this, and I'll send the PDF to your coordinator, so you can have a look at them in some detail. So at around about the same time as our Andromeda study, Philip Lubin at University of California, Santa Barbara, wrote a roadmap to interstellar flight. It was published in the academic journal of the BIS, Journal of the British Planetary Society, in that same year. And he proposed wafer sats that could reach a quarter of the speed of light, reaching the nearest star in 20 years. And he also talked about heavier payloads, although at much lower speeds. And he was aiming for a common laser push infrastructure that could accelerate lots and lots of different types of probes. And that was really the founding paper of the Breakthrough Starshot work, and he's still involved in that. So, Breakthrough Starshot was founded by Yuri Milner, who made a lot of money out of mainly PayPal, I think. He's a general investor and entrepreneur now, I think. The initiative, the Breakthrough Initiative, was supported by Stephen Hawking, who was there at the launch event. And the executive director is Pete Warden, who's ex-director of NASA Ames Laboratory. And he was the person who bumped into Kelvin in California back in that same year and asked us to do the Andromeda study. The chair of the advisory board is Avi Loeb, who's the head of the astronomy department at Harvard. And the advisory board included Kelvin, of course, Martin Rees, the Astronomer Royal, and the late, much lamented Freeman Dyson. And if you've not heard of him, then look him up. A remarkable innovator and thinker. And so, what are the parameters of the Breakthrough Starshot probe as envisaged at the moment? We're talking about something centimeter size and only a gram or two mass. We're still talking about a radioisotope thermal generator as the power source, a camera payload, a sail about 16 square meters, and then a massive array of beam steerable lasers on Earth of a combined power out of about 100 gigawatts, which is about twice the UK peak power generation. We're talking of achieving a speed of 20% of the speed of light to reach Alpha Centauri in 20 years. The spacecraft cost is comparatively small, and you might quite possibly launch a lot of them in a single carrier rocket and then point the beam at them successively to accelerate them away. So we're talking about thousands and possibly tens of thousands of very small spacecraft. So what is Glowworm about? It's under development by nominally separate organizations, but in fact essentially the same organization, and the difference in name is because of the regulatory situation in the UK, which is very sparing with the name Institute. We're going back to Companies House to have another go at changing our name to Institute in the UK, but that's not a hold up to what we do, and we are the Institute in the USA. So we're aiming to conduct the first demonstration of a laser sail in low Earth orbit. And the way we'll do it is to put up a CubeSat, which deploys a small, what we call a femto satellite, of less than 100 grams, a sailcraft, similar lines to the breakthrough Starshot idea, but obviously much simpler, less refined, something that we can do relatively soon. So we put it into a sun-synchronous orbit, so a nice convenient orbit. We're at the early stage of development, but here's the goal. We're aiming to get a 10-kilometer orbital semi-major axis increase. We're trying to raise the orbit by 10 kilometers of the sailcraft. And we're still looking for funding, although we've got a significant amount of funding already. So we're not scraping the bottom of the barrel funding-wise. We certainly haven't got the funds to do a launch yet, but we've got a significant amount of money in the bank to do work preparatory to that. And we have a roadmap. We have a series of development steps. And we have a number of organizations involved. ChipSats are a new idea, and tiny spacecraft that are essentially just pieces of semiconductor chip with a little bit of something added to them are becoming much more viable and much more interesting. And we're aim to build that community. We delivered a ChipSat teaching module, National Space University in Strasbourg back last year, working with breakthrough initiatives. And we've got ChipSat development activities at the Technical University of Munich and at Drexel University in Philadelphia in the USA. So breakthrough initiatives are engaged with what we're doing. The ISU is supportive. Drexel and TUM are doing work. So what will happen? Deploy that femto satellite will attempt to achieve that goal. We've looked at two ways of doing it. A passive way, where the CubeSat remains in the initial orbit and raises the orbit of the sailcraft periodically. And a chaser, where the CubeSat actually propels itself by conventional means and maintains constant separation from the sailcraft. And that's the one we're going to go for, and I'll tell you why as we go forward. We're using the NASA General Mission Analysis tool to work out how we do this. So here's the GMAT results from that NASA tool. If we use the passive concept, we find that for a sailcraft like that, if we're talking about low Earth orbit, then the drag from the remaining atmosphere is too large. We might need 5 years to achieve significant raising of orbit, even in something higher than a standard low Earth orbit. So it looks like the chaser concept might be possible, but not the passive one. So assuming we can maintain perfect separation between the CubeSat and the little sailcraft, and we apply thrust continuously, we work out the thrust needed to complete the mission within 50 days. And here's the model that we get with the usual number of points of the line on a graph, and then a nice straight line drawn through it. I can remember doing it in my physics labs at school, reasonably straight line. And we calculate the thrust to achieve that objective. And we've got some requirements on both the CubeSat and the sailcraft. And I'm not going to go into detail at that, but things like how we aim the laser with very high pointing accuracy at the sailcraft, for example. And a component breakdown of the items we'll need to deliver it. And as you'll see, quite a lot of them are off-the-shelf items. They're things that are available already. A couple of things from Clyde Space up in Glasgow, for example. And the conclusion we come to is that Glowworm is a promising potential laser sail demonstrator. We do need to use the Chaser concept. We might have to have a 3U CubeSat. The standard CubeSat form is 10 centimeter cube. We may have to build something 3 times that size, or maybe even 4. Design work is continuing. So that's Glowworm. And we're aiming to, we've already selected the Chaser option. We're doing modeling and configuration. We're doing thermal analysis. We're constructing a prototype for the sailcraft. We're beginning to do that. We're doing detailed design of a laser system. We're thinking about a ground station for the mission. And there's lots and lots of refinement work to do. But what else is there to stop us sending laser push probes to the nearest stars? The light sail design is a very serious challenge. There's much more detail about this on the Breakthrough Starshot website. If you take a look there, they've got a whole list of things. These are the key ones. These are the ones that are really potential showstoppers. So light sail design, we've got to get that very, very high percentage reflectance and great stability. We've got the need for those gram scale components, thrusters, cameras, processors. We've got to scale a radioisotope thermal generator down to a tiny thing. Resilience under acceleration, because we've got a ground-based beamer, the acceleration has got to take place in a very short time window while the unfortunate habit of the Earth turning means that the beam can only point at the sailcraft for a relatively short time. The probe has got to be able to stand collisions with the interstellar medium at 20% of the speed of light, so that's no small challenge. We've got to think about reliability over 20 years, and we've got to think about pointing for both the camera and the downlog. And I just put there at the bottom a thing that applies to all propulsion concepts for interstellar probes, and that is what is called the weight issue or incentive trap, which is that given how long it takes to get to the nearest stars, and the longer it takes, if you take 20 years, then you're probably okay. If you take 50 years, then it gets worse. The longer it takes, the more likely it is that somebody will come up with a technology that will overtake you, and therefore you never try. So that is always there with interstellar missions of any significant duration. So other challenges. So the sail has got to maintain integrity and stability. The beamer costs are very substantial, as you can imagine, with that 200 gigawatt requirement. We've got to point it. We've got to think about the atmosphere effect. We've got to generate the power and store it. And the cost of the power to deliver to the beamer is getting more and more an issue. And there might be some justification for going to a space-based system, partly for that reason. So a space-based laser push array rather than a ground-based one. Keeping the thing cool, range safety and political clearance. If you've got a 200 gigawatt laser beam pointing into the sky, then anything between it and the target cell is not likely to have a pleasant experience. So you've got a problem there. And you also want to make extremely certain that the beam is pointing in the right direction. A longer range challenge is to slow down, because all these probes, Daedalus and the near-term sailcraft, would not slow down. The idea of Project Icarus was that the vehicles would slow down, and that's why Icarus Firefly is a 100-year mission rather than a 50-year one like Daedalus. But there are possible ways of doing it. you can use the interstellar medium. You can use magnetic or electric sails using the solar wind or the magnetic field of the target star. But that's all very early stuff. And then there's the problem that is closest to my heart as an old communications engineer, and that is the link budget. It's very hard to get a signal from a very small probe back across 4 light years. Can we use the sail as an antenna, as a sort of reflector? Can we use swarm tactics to get the effect of multiple probes all assisting one another? Can we use the beamer as a receiver? And I'm currently in the process of writing a review article on the subject based on the more detailed academic papers on this whole business of the link budget. Okay, so switching tack, a little bit about IFRS Project Lyra. Here we're talking about missions to interstellar objects, and this all starts with One-Eye Oumuamua, which I'm sure the astronomical people amongst you will have heard of, and it remains a mystery. It's clearly not a conventional comet. It's almost certainly not an artifact, despite the fantasies of some of the more wild media and some of our more imaginative scientists as well, including Avi Loeb at Harvard, for example. Although he's not wedded to the idea, he just speculates that it might be a possibility. But it behaves very strangely. Two-Eye Borisov, the second interstellar object, is simply a comet and doesn't exhibit any significant behavior different from a conventional comet. So it's quite striking that we've seen two. Oumuamua was found by the telescope on Mauna Kea in Hawaii, that's mainly concerned with objects that might threaten the Earth. But it was only spotted as it was leaving the solar system. It had swung around the sun and was heading back out again by the time it was spotted. Borisov was picked up by an amateur astronomer of that name in Romania, I think. So what can interstellar objects teach us, and how do we learn it? Well, in essence, we've got to go there. We've discovered a lot more about Pluto by going there than we ever did by pointing telescopes at it, and the same applies with interstellar objects. So here's the questions we need to answer, particularly about Oumuamua. First of all, it's long. Its length to width ratio is about 5:1. It's tumbling, and there's some jargon there, but I just, from my point of view, it's tumbling, but it's not breaking up, so it's not fragile. It's quite a strong body in that sense. It's accelerating away from the sun, as comets sometimes do, but the tumbling motion is unchanged, so whatever it is, the thrust vector appears to be through the center of gravity. There's no associated meters and no visible outgassing, so it's not a conventional comet. And I quote here an astronomer of world renown, and certainly UK renown, who has a couple of times I've heard her say in lectures that she's given that I've attended, what astronomers are looking for, and in fact perhaps scientists in general, is that phrase when they see something and they say to themselves, "That's funny." And that's what she said, perhaps not literally, but in her head, when she saw the wiggle on the pen chart back at the Cambridge radio telescope, way back, which was the discovery of the pulsar. And Jocelyn Bell-Burnell, whose name I'm sure the astronomical people amongst you will know, is a very striking lecturer and somebody to go and see if you get the chance. But she uses that phrase, "That's funny," and there's certainly something funny about Oumuamua. So what are we talking about in terms of the project? We've got 3 principles. There are others involved, but 3 principles involved in this. Adam Hibbard, who is a former rocket engineer, worked on early Ariane rockets. he's developed a mathematical toolkit called Optimum Interplanetary Trajectory Software, and that's how we can do mission predictions for various ways of overtaking those sort of objects. And most recently, we've actually done a paper about a very near-term mission to Venus, given the discovery of phosphine in the atmosphere. So the Project Lyra team is well set up to do fairly rapid mission planning with the assistance of Adam's OITS. Marshall Eubanks is an American ex-Jet Propulsion Laboratory and US Naval Observatory, and he's a bit of a polymath. And he's been involved in this virtually since the beginning. Andreas Hein is our technical lead and exec director. He's a German guy, Technical University of Munich again, but he's a lecturer at University of Paris-Saclay in France. Now here's an animation. I hope this works. This is an animation based on Adam's OITS software. This doesn't always work, but if it does, it's quite striking. So here we go. There's Oumuamua, and there's the Earth rotating around the Sun, orbit of the Earth. So I've set the animation going. So we're talking about quite some time in the future. And here goes the probe, launched from Earth. Here's the Earth spinning around its orbit, and there's a propulsion maneuver out there at apogee. The probe then comes back to intercept the Earth, gets a gravitational kick from it, which takes it out to Jupiter. And then something very strange happens at Jupiter, although this is not just Adam's idea. And what you see is that actually it's doing the opposite thing. It's losing momentum to Jupiter and it's plummeting towards the Sun. And when it gets there, you'll see a big scale change. So there it goes. So what's happened is that it's gone around the Sun very close, and it's fired a rocket at perihelion. And Hermann Oberth invented that, and it's called an Oberth maneuver, and you get a hell of a kick by doing that. And then you gradually overhaul Oumuamua. It's still going away from the Sun, and of course the probe is now slowing up as it approaches, but it never actually intercepts. It does a flyby, and there it is at Oumuamua. And I think we managed to make that work. So the next thing is I've got to go back to my slides. So I'll just kill that off and we'll go here. Right. So that's it essentially. Here's some references. Salkowski, an article in Principium. Forward, the original paper. Lubin, the paper I mentioned, University of California, Santa Barbara. And there's an open access version of it at that NASA site. Zachary Burkhardt, who did a substantial study on Glowworm at the International Space University. So that's the largest paper about the Glowworm project as a whole. Our website page for Glowworm, the Andromeda study, which is on Archive, Breakthrough Starshot. The best place to start on Starshot, if you're really interested, to look at Kevin Parkin's system model. That's on Archive, and I think now in Astronomical as well. Looking at fusion propulsion, the Icarus Firefly idea, there's a very useful article by my co-editor Patrick Mann, which appeared in Principium back in 2018, and it's also available on the I4IS website as a separate web page. And the slow down issue, one of our other team, who's a solar physics researcher at University of Warwick, Tishrin Mater, wrote a piece for Principium about how to slow down, based on some ideas from Claudius Gross at the Goethe University of Frankfurt. There's some papers on Lyra. There's some more recent ones than that as well, but there are those three. They're all on archive. The first, and I think the second, is now in Acta Astronautica, the peer-reviewed publication. Some other papers on interstellar objects. The Avi Loeb paper with one of his postgrad students about solar radiation pressure on what would have to be a very thin Oumuamua. And an early paper by Seligman and Laughlin, both of whom were at Yale. I think one of them moved on now, about feasibility and benefits of in situ exploration of Oumuamua objects. So lots of references there, and as I say, I'll send the PDF to your convener. So what else does I4IS do? We have a long-term ambition to enable robotic and human exploration and eventually settlement of nearby star systems. We're really an organisation with both a very long-term vision and some very short-term practical things to do, and lots of things in between as well. And we're aiming at outreach. We do work with schools and universities, notably several successive sessions with the master's programme at the International Space University in Strasbourg. Doing outreach is what I'm doing right now. Research and development, in particular Glowworm. And the team has been based mainly in UK, France, Germany and the USA, but there are some other countries involved as well. And we work with other organisations, the BIS, of course, which is our parent organisation. Tennessee Valley Interstellar Workshop, who are about to change their name. The Tau Zero Foundation, as I mentioned earlier, Breakthrough Starshot, of course. A new organisation, Limitless Space, that is driven by a guy called Sonny White, who's was formerly head of one of the NASA Blue Skies research groups called the Eagle Works. He used to work on that. Icarus Interstellar, which is the foundation body for the Project Icarus. And of course, NASA and ESA. And ESA held their first interstellar probe workshop last year at Noordwijk, at STEC in Noordwijk. Principium, which is what I edit, and it's free. And there's a link to sign up to receive it. And I particularly like the front pages, work by David Hardy, the veteran space artist on the left, and by Michel Lamontagne again. He's not only an engineer, he's a very decent artist as well. So that's Icarus Firefly in assembly in low Earth orbit on the right-hand side. So, comments and questions. Shall I stop share now? I think I probably should.
Right. Well, thank you very much for that. People can put their audio and video back on as they want to now, and you can put questions in the chat channel, or you can raise your hand either digitally or in reality. Okay, I've got a question from Roger Moses there, so you need to let's unmute you.
Okay, I'm not au fait with what's going on at the moment, but I looked at this stuff 20 or 30 years ago and got very interested. And then there were a lot of, 20 years ago, there were a lot of experiments in low Earth orbit on the stability of light-propelled spacecraft, mainly from the sun. And the results were not great, to put it mildly. The Russians put up quite a big reflector, it's 100 meters.
Right.
But it was unstable. It couldn't maintain position. It kind of randomized itself. But what I'm saying is why use a really big laser that we don't have instead of using the sun, which is 10 to the 20 times as much light output. I mean, it doesn't matter if it's not very efficient when you reflect it, but there's a hell of a lot of power there.
Yeah, I think the problem with the sun is that the energy density, per square meter to fall onto a sail is insufficient.
Yeah, but that's one
reflection. Acceleration that you need.
Yeah, but that's one reflection cures that, ideally, but it'd probably be 2 or 3 to get it down. And all these things interact. The systems engineering of the whole thing is horrendous. But unless you can maintain a very narrow beam width and a very accurate pointing accuracy, you're on a hiding to nothing.
I couldn't agree more. I mean, that's why Yuri Milner's spending $100 million in design studies. But these are major challenges. There is no doubt of that.
Oh yeah, I mean, it's about the most difficult problem you can think of.
The reason why this is going forward is that it looks like it might be feasible, and at the moment it's the only way in the relatively short term. Now there are differences of view here, and I'm not an expert on this. I'm a software engineer, mobile telecommunications engineer. So the downlink is more interesting to me, and I think is as much of a challenge as the propulsion system. But anyway, leave that aside.
I'd agree with you there.
I think that there is much to be said for building the whole of the infrastructure to support this in space. It will take longer, of course, but once you have significant in-space manufacturing, and that is not as far away, certainly not as far away as being able to build something like the Daedalus or Icarus craft. Once you've got that capability, and you're using local resources, you're using what is called in situ resource utilization, and you've got a manufacturing capability for anything that's of significant mass, then your ability to build things like very substantial solar power farms, and the substantial infrastructure needed for big, powerful laser batteries, the cost starts to go down and down and down because you're building it out there. And of course, if you do that, you've got the tremendous advantage that you're not on a rotating Earth. So your instantaneous beam power is that much less because you can keep pushing for hour after hour, day after day. Of course, the inverse square law gets to you in the end, but you can run the beamer for much longer and therefore require less peak power. And that's certainly the early work that I4IS did was along those lines. But Yuri Milner's in a hurry. He wants to do something that will happen, he hopes, in his lifetime, I think. So doing it from the ground gives that possibility, but it's only a possibility. But the work that's going on will almost equally support a space-based infrastructure.
Yeah, I mean, the attraction of the light-driven spacecraft is, and it drives you to a very light vehicle.
Yes.
My worry is that you get a very minimal capability probe.
Well, I recommend that if you're a communications specialist, then read the papers by Messerschmitt and et al. Who's University of California, Berkeley, emeritus professor, and Kevin Parkin, who's an independent consultant who worked for Breakthrough Starshot, about the downlink. If you're not a communications engineer, then read the article that I'm writing at the moment, which is intended to be accessible to somebody who's reasonably numerate, but is not a specialist in that area. And the downlink challenges are interesting, but I think are probably capable of being overcome. But it's not easy. I think if Tony wants to call out who's to speak next. I think we've got
thank you very much.
Yes,
it certainly isn't easy.
Yeah, we've got a few questions backed up now. I've noted that David and Brian are both in the queue for questions, but I wanted to go to Deepali, who put one in the chat room earlier. She asked where the launch is proposed to be from. I wouldn't have thought the location of the launch was that important at this stage, but over to you, John.
The idea is to put the tiny sailcraft, probably quite a lot of them, into a single booster and deploy them in space, and then point the laser at them, laser bank at them selectively. So, in essence, you choose the launch site to be compatible with wherever the laser array was. Yeah, it's relatively insignificant. The second question was about funding. At the moment, there is $100 million, and I don't think it's being spent very quickly because at the moment it's all paper studies. But that's a very substantial amount of money that Yuri Milner's put in there. Funding for the actual implementation is a different matter, of course, and would require several times that. So probably several orders of magnitude more than that. I think we're talking about something like $20 billion or something like that. But probably less than the American Artemis program to go back to the moon. That's the sort of order of cost they're looking at. I mean, they're looking at all these aspects.
Right.
So I think there were two people with their hands up. But if you
so
want to...
before we go on, I just wanted to pick up on what you said about references. I don't have a list of the participants in this lecture. So what I need you to, if you want the list of references, you must write me an email to ask for it. And when I get it from John, I'll pass it on. So is that okay? Is there anyone who doesn't know, who hasn't got access to my email address? I mean, I've given it out on a lot of communications. So if you email me, I will reply with the list of references. Now, going to David, please.
Can I just ask?
Well, you've had a couple of questions, Deepali, so can I keep you in the background for a moment and pass on to someone else now, please? David, what was your question?
Oh, hi. Yeah, I was just interested in the sort of propulsion side. Obviously, there's a principle in physics of the conservation of momentum. A rocket, the momentum of the gases coming out the back of the rocket always equals the change in momentum of the rocket itself. With the light, do you get an equal and opposite reaction force in the beamer itself? And if so, would that be a problem if the beamer's in space as well? Would you have to counteract that? I assume the beamer would be a lot heavier.
Yeah, I mean, if we're talking about a beamer that's maybe a few thousand tons, if it's on the Earth's surface, then you're talking about the Earth, so that really is insignificant.
Yeah.
If it's in space, it would still be very much more massive than the individual sailcraft. Yeah, I think you're almost certainly right that there is an equal and opposite reaction, and that's sort of illustrated in the that factor of 2 in Robert Forward's lightsail equation, because in fact if you get perfect reflection of the photons, then you exchange double the momentum of the incoming photon.
Okay, thanks. Yeah.
Brian, you need to be. Brian, you're muted still. You need to. Brian, you are muted. You need to unmute your.
Yes, I'm trying to. What do we know about drag in interstellar space from dust and gas on a very light object traveling at very high speed?
Yes, I think it's almost certain to be significant. But as I understand it, it would not be enough to make a big difference to the transit time. But one of the interesting things is that some of the studies that have been done as part of the Starshot project, there's an issue about having enough power to drive the communication for the downlink, and one of the ways of doing that that's particularly considered in the Kevin Parkin paper on the subject is the idea of using the collision of the interstellar medium with the vehicle to actually generate power. I don't know if you recall the diagram of the Daedalus probe, but it had a big flat circular shield on the front of the payload, and if you look at the Daedalus papers, there's a lot of calculation about the erosive effect of the interstellar medium in those papers, and of course the Daedalus probe suffers from exactly the same potential problem of being slowed by the interstellar medium, and the calculations that the Daedalus team did were based on limited information, but I think things have not significantly changed in that respect in terms of knowledge of the interstellar medium, and the effects are not likely to be significant. They will be as significant as eroding the probe, so you need shielding of some sort. They don't seem to be significant in terms of actually slowing it down much.
Right, is there anyone else, or shall I go back to Keith, a question from you.
Yes, don't you have a problem with the half-life of the nuclear heat source with your RTGs?
If you only take 20 years, then no. Voyagers are still running on an RTG after 40 years. So even if you just use the standard plutonium-238, I think it is, the Voyagers have still got enough power left in their RTGs to still be able to transmit, and that's after 40 years. And these probes
yes,
are only 20 years.
Yeah, but the power's dropped off significantly. We on LSEP, we could no longer maintain reasonable operations after 7 years on the moon.
Right. Well, that's interesting, because I'd like to see the contrast between that power source and the power source on the Voyagers.
We had a Snap 27.
That's not a reactor, is it? It's still
no. It's a plutonium thermoelectric generator.
Right. So it's in terms of the physics, it's exactly the same as on the Voyagers. So
yes,
it's interesting that it wasn't sufficient. So maybe what we're talking about is with the OLSEP, the power demands were really quite substantial, and it wasn't intended to last very long. I mean, clearly you've got an exponential decay curve if you're using an isotope power source. But as I say, if the Starshot idea of doing the 4 light year transit within 20 years works out, then the RTG lifetime is not a serious issue, it seems to me, given that the Voyagers have lasted 40 years.
Yes, but you've got to develop a very small one. Have you thought about this new development of the beta voltaic carbon-14 diamond cells, which have been developed at Bristol?
Yeah, that is something that came into the Andromeda study. If you look back at the Andromeda study papers, they looked at a rather wider variety of possible power sources than the papers I've seen from Starshot. So if you look at the I4IS Andromeda paper, it's in the references. I'll send the PDF to Tony, so you'll have not only the slides, but you'll have the 2 pages of references. If you have a look at that, I'm pretty sure it does include that as a possible option. And I think it's actually. Sorry, say again.
Yeah, go on. Sorry.
Yeah, I mean, as I say, a wider variety of possible sourcing. If I remember correctly from that study, something like that sounded like that, I couldn't be absolutely certain without consulting it, was actually the selected preferred source of power for the Andromeda study back in 2016.
Yeah, they're certainly looking at a very long life, much longer than normal RTGs.
Right. Yeah, I mean, there's been other studies. There's been thinking about americium, which has a much longer half-life, but of course has a much less density. And everybody worries about putting isotope sources up on rockets, because what happens if they fall down? You know, and it's a it's a worry.
If I could put in a question at this point, what materials are you looking at for a light sail then? Because that was one of the things that you mentioned was very challenging.
Yeah, I haven't looked at that. I have to confess. So I don't recall. If you the place I always look for this sort of thing is either the Breakthrough Starshot website, which isn't always that helpful, but if you use Google Scholar to search papers, including ones that have not yet been peer reviewed, so they're on things like Archive, they're on preprint websites. That's where you'll find the thinking going on, and there is certainly work going on about that. And there are materials that have the required reflectivity. The big worries I've seen recently have been not so much about the reflectivity as about the stability in the beam of the sail. And in fact, I think I saw just a few months ago a study that suggested that it might be better to build the sail as a spherical object. This sounds counterintuitive, but it does seem to be an attractive option, and it has the merit of possibly behaving in a more stable manner in that beam.
Right. Right. Roger, it's a question from you. You need to... Roger, you're muted. Roger, you're muted. You need...
There we are. Just a remark that the stability of the reflector on the spacecraft at its attitude in space can completely wreck the mission. So somehow you've got to be able to keep the spacecraft oriented within the tolerances required by the optical laser beam system. Otherwise, it's going to go off to the side somewhere.
You're talking about the downlink now?
No, I'm talking, and the downlink, that would just be another consequence. I'm talking about the mechanical trajectory.
Right.
It's the,
one of the things
which is the argument for the spherical reflector.
Yeah. I think one of the things that's interesting and sort of fundamental about this is that like all these things, the aperture of the instrument you're using, whether it's a data transmitter or a big, obviously much greater power, or whether it's a receiver, the aperture governs the degree of selectivity. And if you look at the polar diagram that tells you what the gain is at different points of where the antenna is pointing, just in simplest terms, the bigger the antenna or the mirror or whatever it is that you're using, the narrower the beam. So your beamer on the ground is potentially, at least as I understand it, a rather more focused thing than, for example, the very much smaller laser you'd be using for the downlink from the vehicle as it passed Alpha Centauri. And there's interesting questions about whether you might more sensibly put the receiving antenna for the downlink in space rather than putting it on Earth as well. Similar arguments in some ways to the question of where you place the beamer. Tony, there's a couple of questions on the group chat.
Yes. Well, there's one from Deepali again about permissions for positioning the building of the probe in space. I don't know if you.
Yeah, I mean, I think the where the probe is in space is rather secondary. It's the issue of where you put the beamer on the ground, and what the damage might be if something went wrong, in particular in the pointing or scheduling of the beamer. That's the real challenge if you've got a ground-based beamer. I mean, of course, if you've got 200 gigawatt laser bank up there, then anything that powerful is a weapon. I mean, the thing to remember is if you're talking about powers like this, then everything can be repurposed as a weapon. If you look at the Daedalus first stage engine or the Z-pinch engine on Icarus Firefly, if you point them in the wrong direction, you can do a hell of a lot of damage. And the same applies to that beamer for the breakthrough Starshot sailcraft idea. You're talking about powers that as I say, are dangerous. So you need to be very careful about them.
I thought that the beamer would be where the launch would happen, not on Earth, not ground-based.
The breakthrough Starshot idea is to put the beamer on the ground. Okay. That's one of the reasons why the acceleration has to be so violent, because the Earth, unfortunately, tends to rotate. So the beam can only point at the sailcraft for a relatively short time. There was another question from Tom Fletcher.
Yes.
Yeah, Glowworm will be travelling a lot faster than Voyager. Well, that's not Glowworm is an experiment. Glowworm is a low Earth orbit experiment, but taking that to mean the proposed Starshot probe or anything like it, the Andromeda idea or the ideas that were put together in the Dragonfly studies. Yeah, travelling a lot faster than Voyager at 20% the speed of light. The impact on the life of the power source, I don't think is significant. One of the interesting things about, I guess you're talking about relativistic effects. Relativistic effects don't look very significant until you get up to like 30 or 50% of the speed of light. It's a very non-linear effect. I mean, it will be measurable, and you'd have to take account of it, but it doesn't make much difference to engineering feasibility. The relativistic effects. Interesting, you're talking about Voyager. If you're interested in a faster Voyager, have a look at the Johns Hopkins University Applied Physics Laboratory idea for something they call their interstellar probe. It's not an interstellar probe at all. But what it is somebody described it as Voyager on steroids. It's essentially it's got the same target objectives in the Kuiper belt as Voyager or perhaps New Horizons. But the striking thing about it is that it intends to use that Oberth maneuver again as the animation that you saw. So you lose momentum, in fact, potentially around Jupiter, as Adam Hibbard's animation showed, and you swing around the sun as close to it as you can afford with heat shields and all that sort of stuff, like the Parker Solar Probe, very similar technology from the same people, in fact, from Johns Hopkins Applied Physics Laboratory, and you fire that rocket at perihelion. And you get something that does something similar to Voyager, but it only takes about 10 years to get out there. So it's traveling a hell of a lot faster than Voyager. And of course, it's a much more substantial probe with much more advanced instrumentation. So what Ralph McNutt and the guys there are talking about is a super Voyager, but nowhere near the speed of light, no significant fraction of the speed of light, but they are talking about something that is pretty fast. That's quite interesting. I've heard the guy speak, Ralph McNutt, Pontus Brandt. He does a lot of work on that. I've heard him speak too. Yeah, there are a bunch of hot shots at Johns Hopkins. But that's what we need to do this sort of thing.
Yes, I'm wondering if I could ask you to go over the chaser concept. That was
okay. Yeah. I mean, ideally, what you'd like to do would be to get as close as possible to the idea in both the Andromeda study and the old Dragonfly studies, and the Starshot idea, which is that the beamer doesn't move. The beamer is either fixed in space, as in Andromeda, or it's fixed on the ground, as in Breakthrough Starshot. But what the calculations have shown using that NASA modeling tool is that you can't get the relevant orbit rays by doing that. So what you have to do is you have to cheat slightly. You have to get the CubeSat, which is carrying the laser, to actually raise its own orbit so that it stays at a constant distance from the little sailcraft and keeps pushing on it with the laser. So you're still demonstrating the concept of laser push in Earth orbit, but you're not doing it from a fixed platform. You're doing it from a moving platform. That's what was discovered to be necessary to achieve it with the technology and the limitations that we have at the moment.
Okay, do we have any more questions?
I just got a comment there. And I can see the sense of using the beamer, satellite, but it kind of negates the whole thing if it's following up the backside of the reflector. I mean,
yeah, it doesn't negate the whole thing.
How far are we talking the separation? Kilometers?
I haven't looked at the detail of that. You need to look at Zachary Burkhart's paper. Is probably the best source for that, and it's in the references.
Yeah.
No, I agree.
What it does beyond the solar
it would be a better demonstration if we could use the fixed the little beamer being fixed in its orbit, but we're still representing the principle. It's only a question of distance, and it's just a question of factoring in the inverse square law. The principle is the same. You'd have to have a laser of greater power in order to achieve the required orbit rate with a fixed CubeSat. Sorry, go ahead.
I can't see what it's doing that the solar propulsion sails haven't done already.
It's doing it with an artificial source, not with the sun.
Yeah, but if you're putting the artificial source up the backside of the test piece, I don't see what it's doing.
Well, it's doing slightly more than doing it in a lab on Earth.
Well, it is, but you've already done it with sunshine.
You've done it with
sunshine.
Oh, you mean in the case of things like Icarus and the Planetary Society demonstrator?
Yeah.
Yes, that's true. That's true, but it's not been done with an artificial source in space. It's not been done.
I don't see what new it's demonstrating.
It demonstrates things like pointing the laser, getting the relevant reflectivity from an artificial source rather than from solar photons. It demonstrates the ability to build very, very tiny sailcraft, very much more, very much smaller than for example, either the Planetary Society demonstrator or the Japanese Icarus probe. So you're getting close to what Starshot would have to do in terms of the miniaturization issue, because there's a whole series of things that you're checking out and demonstrating that have not yet been done. Yeah, I mean, of course it's got limitations, but it's demonstrating and testing quite a lot of things towards the eventual sailcraft that we're hoping might be launched. One of the things that happened to me when I first got involved with this, I've been a member of the British Interplanetary Society for a long time, was when I bumped into Kelvin Long and Rob Swinney, who were the two founders of I4IS, at the BIS, and they said that they were starting this new outfit. I was very excited by it, and still am, as you can possibly detect. But one of the things I thought, well, at my age, and I'm now 73, at my age, I'm not worried about whether it's going to happen in my lifetime. I know it isn't. Whereas some of the younger people possibly are worried. They think, can I live long enough to see this launched? And I think that's what Yuri Milner wants to see happen. He wants to see it launched in his lifetime. Of course, he's got a lot of money, so he can afford to indulge his dreams. But now I've got to the stage where if I lasted as long as the Queen or the Duke of Edinburgh or something, way into my 90s, then there's a distinct chance that there is a possibility, at least, that there will be the first launch of something like Starshot. So I'm back to worrying again now. That's sort of ironic, really.
Thank you.
Right. Well, we've sort of reached a natural end now. I'd like to say that this has been a tremendous tour through a whole bunch of quite speculative technologies, but on which experiments are being done and which will result in something happening. And I think that makes it all very exciting. So let's all thank John Davies very much again for a very interesting lecture.
Thank you very much. And do look at the PDF when Tony sends it to you. Look up the references and subscribe to Principium. We need more readers.
Okay, that's great. Don't forget to send me your email address, because otherwise you won't get the references.
Yeah. Oh, sorry. You're talking to the audience now rather than me. Okay. Yeah. Yeah. Sure. Right. Well, I will drop out at that point then. Yes, I think I've got my dinner waiting for me, so
I'm going to click on end, which will, I'm told, finish the recording.
Okay. Thanks very much. Look forward to that.
Thank you very much.
Thanks, everybody. Thanks.
Thank you, Joe.
Thank you, Tony. Thank you very much, Tony.
Thank you, Brian.
Well done.